Most people think the future of AI is just bigger GPUs and larger models. But there's a completely different direction that might matter even more, and that is neuromorphic computing. Today, I want to walk you through what it is, why it's exciting, and how it could reshape the future of intelligence. My name is Venkat Margapuri, and thank you so much for joining me here today. Right now, all the attention is on scaling, bigger chips, bigger clusters, and bigger training runs. But the really interesting question is, what happens if the future of AI doesn't come from scaling the old approach, but from adapting a totally new kind of hardware inspired by biology? That's what neuromorphic computing is all about. Neuromorphic computing is basically the idea of building hardware that works the way neurons and synapses work in the brain. Instead of doing continuous math all the time like a GPU, these chips fire tiny bursts of activity almost like spikes only when something needs to happen. Memory and processing happen in the same place and everything runs in parallel. It's a fundamentally different model of computation compared to the one that we're typically used to. Traditional computers follow a very rigid structure. They're sequential, they're power hungry, and they keep memory and computation in separate places. The brain is the complete opposite. It's massively parallel, incredibly energy efficient, and memory and compute are deeply intertwined. So when we try to simulate a brain on a normal computer, we're forcing the wrong tools under the problem. And this difference shows up clearly in terms of energy use as well. Your brain runs on just about 20 watts, barely enough to power up a dim light bulb. Whereas a large language model, on the other hand, relies on enormous GPU clusters consuming millions of watts. That gap is why neuromorphic computing is so exciting. If we can get anywhere near biological efficiency, everything changes. The brain has a couple of genius design tricks that make it work the way it does. First, neurons are mostly quiet. They fire only when needed. Second, communication is fast and event-driven. Third, learning happens continuously, not in giant training loops. And finally, memory is distributed everywhere, not stored in one big block like random access memory, or otherwise known as the RAM. Neuromorphic hardware tries to borrow all of these ideas as well. There are a few areas where neuromorphic computing can really outperform GPUs. One is real-time learning, adapting instantly to new information without retraining huge networks. Another is low-power robotics, like drones or wearables that need to be fast but cannot afford heavy energy use. And then there's edge AI, devices that need to think locally without sending data to the cloud. Neuromorphic chips are a natural fit for all of this. Some serious efforts already underway in the context of neuromorphic computing. IBM's True North chip was one of the earliest large-scale neuromorphic systems with around 1 million neurons. Intel's Lohi 2 is designed for experimenting with spiking neural networks, and in Europe, the Human Brain Project built hardware meant to model brain-like computation at scale. There are also startups exploring analog synapses, memristors, and even photonic approaches. It's a young field, but the diversity of ideas is just amazing. So the natural question is, are neuromorphic chips going to be GPUs? And the answer really depends on the kind of AI that we want to build. GPUs are fantastic at today's deep learning, dense matrix map, and huge batches of parallel operations. Neuromorphic chips, on the other hand, So to the question of will neuromorphic computing replace GPUs? The answer is, in the short term, no. GPUs are way too good at powering current transformer-based models, but if AI starts moving towards architectures that behave more like real biological intelligence, systems that are sparse, constantly learning and responding to real-time signals, then neuromorphic hardware might start to become incredibly important and significant. In the long run, we might see a split. GPUs might be used more for training big models, whereas neuromorphic chips might be used for real-time intelligence. So long term, I think the most powerful computers may not be giant GPU clusters. They may be systems that look and behave a lot more like biological networks, adaptive, efficient, and always learning. Neuromorphic computing is one of the first serious attempts to get us there. So if you enjoyed this breakdown and want more deep dives into frontier technologies, make sure to subscribe or follow along. There's so much happening at the edges of AI and computing, and I'm excited to explore all of it with you. Thank you.